Okay, perfect. Well, welcome everyone to this year's first session of the virtual seminar on geometry with symmetries. It's a pleasure to have Daniela Di Donato from the University of Pavia, who will talk about rectifiability in Carnot groups. So thank you, Daniela, and we very much look forward to your talk.
Thanks. Thanks, and thanks the organizers to give me the opportunity to speak. Today I talk about rectifiability in Carnot groups. This is joint work with Antonelli, Donne, and Le Donne. In the first part of my talk, I recall the notion of Carnot groups, rectifiable set in Rn and in Carnot groups. Then I give the equivalence between C1H regular surfaces and intrinsic Lipschitz graph. And finally, I give a characterization of C1H regular surface in terms of suitable quick solution of PD system. This PD system, in the model case, the first Heisenberg group, is Burger equation. A Carnot group of step K is a simply connected Lie group whose Lie algebra G admits a step K stratification. That means the Lie algebra G is equal to the direct sum of V1, Vk. Satisfy these equalities. We call Vi layer, and in particular we call V1 horizontal layer. V1 generates all of G throughout the commutators. Throughout the exponential map, it is possible to characterize G with Rn, where the group operation is given by the Campbell-Hausdorff formula. The most important fact is that the Campbell-Hausdorff formula is a non-commutative formula. It is useful to know that we can write a Carnot group G equal to the direct sum of G1, Gk, where Gi is equal to Rni, and Ni is the dimension of the layer Vi. So we can write H point P equal to P1, Pk, where Pi belongs to Rni. In Carnot groups, we consider two important families of transformations, the intrinsic left translations and the intrinsic dilations. The intrinsic left translation is a map from Q, from G to G, and type PQ is equal to P dot Q. The intrinsic dilation is a map from G to G, and the delta lambda P is equal to lambda 1, lambda K, Pk. These two families are really important because when you define a notion in Carnot groups, it is important that this notion is invariant with respect to the intrinsic left translation and the intrinsic dilations. Now I introduce the homogeneous norm. A non-negative function is said to be a homogeneous norm if the norm of P is equal to 0 if and only if P is equal to 0. It is one homogeneous with respect to the intrinsic dilations, and the triangle inequality holds. Given any homogeneous norm, it is possible to introduce a distance in G, given by the distance between 2 points P and Q is equal to the norm of P minus 1 Q. This distance is invariant with respect to the intrinsic left translation, and it is one homogeneous with respect to the intrinsic dilations. The topology is the Euclidean topology, but the two distances are not equivalent. So in particular, the topological dimension of GD is equal to n, but the metric dimension is larger than n. In particular, it is equal to the sum for E from 1 to k, I dimension of the layer Vi. This number is called homogeneous dimension, and in general it is larger than n. Now I present a model case, the Heisenberg groups. The nth Heisenberg group Hn with n is larger or equal than 1 is a Carnot group of step 2. With the Lie algebra, Hn is equal to the span of x1, xn2, the direct sum of the span of x2n plus 1. The only non-trivial brackets are the commutator of xi plus n is equal to the last vector field x2n plus 1. So we identify Hn with R2n plus 1. We can write a point P equal to P1, P2, where P1 belongs to R2n and P2 is a real number. The intrinsic dilation of a point P is equal to lambda P1, lambda squared P2. The topological dimension of HND is equal to 2n plus 1. The metric dimension is equal to 2n plus 2. So we know that E, a subset over N, is de-rectifiable if E is the Lipschitz imagine of a subset over D. More general definition, we say that E, a subset over N, is countably de-rectifiable if it is possible to cover it with a countable union of D-dimensional C1 embedded submanifolds, or equivalently, it is possible to cover it with a countable union of the graph of phi-I maps, Lipschitz map, from Rd to Rn minus D. In Euclidean case, the Lipschitz definition and the C1 definition are equivalent. The proof follows from Rademacher theorem, extension of Lipschitz functions, and Vittone extension theorem. The aim of my research is to give the Lipschitz version and C1 version in Carnot groups, and then prove their equivalence. So the question are, what are the dimensional C1 submanifold in G? What are Lipschitz graph in Carnot groups? And which Hausdorff measure do we have to use? I start to recall the definition of intrinsic Lipschitz graph. This notion was introduced by Franchi, Serrapioni, and Serra Cassano, first in the context of Heisenberg group and then generalized in Carnot groups. So, the first ingredient is what is the intrinsic graph. Let W and V two complementary homogeneous subgroup of G, that means their product is equal to G and the intersection is equal to 0. Homogeneous meaning that it is closed with respect to the intrinsic dilation. We say that S is a left intrinsic graph over W in the direction of V, or in short, intrinsic graph, if there exists a map phi from W to V such that S is equal to the set of element A phi A, where A belongs to W. This notion is intrinsic. That means the left translation and intrinsic dilation of graphs are also graphs. Which is the idea of intrinsic Lipschitz graph. Franchi, Serrapioni, and Serra Cassano introduce a suitable cone called intrinsic cone, which the idea is similar to the Euclidean cone, but obviously they are not equivalent. And they say that phi, a map from W to V, is intrinsic Lipschitz if for all point P belongs to the intrinsic graph, there exists an intrinsic cone such that the intersection is equal to just the point P. In the picture, it is possible to watch the model case, the first Heisenberg group, R3. And in the red part, there is an example of intrinsic cone. In the blue part, there is an example of intrinsic Lipschitz map. Intrinsic Lipschitz map are not Lipschitz in the classical sense, but it is true that a map intrinsic Lipschitz is locally 1 over k order continuous, where k is the step of Carnot groups. Intrinsic Lipschitz graph are all-force regular. What meaning? Meaning that it is possible to compare the ball center P with radius R with R power dm, where dm is the metric dimension of W. and W and V are two complementary homogeneous subgroups of G. 5 is intrinsic Lipschitz. Now we present the definition, the Lipschitz version of definition of rectifiability. E is DDM-GL rectifiable if it is possible to cover it with a countable union of intrinsic Lipschitz function phi I from Wi to Vi, where Wi and Vi are two subgroup complementary in G, and Wi has topological dimension equal to D and metric dimension equal to Dm. Now I present the second definition, the C1H regular surface. This definition was introduced by Franchi Serapione and Serra Cassano and then generalized by Magnani. Then I present the equivalence between the two definitions, intrinsic Lipschitz and the C1 version definition. Let x1, xn1 be a basis of V1, the horizontal layer. The horizontal gradient of a map F from G to R is the vector x1f, xn1f. A continuous function f from G to Rk is of class C1H if its distributional derivatives are continuous. So, S, a subset of G, is C1H regular surface of codimension K if K is a number from 1 to N1, and 1 is the dimension of the horizontal layer V1, and it is possible to say that S is locally equal to the level set of C1H map. Moreover, we want that the metric of its distributional derivatives has maximum rank, then equal to K. Now I present the problem in the model case, the Heisenberg groups. E, a subset of Hn, is DH rectifiable, the C1 version, if it is possible to cover it with a countable union of C1H regular surface. The Lipschitz definition uses the intrinsic Lipschitz graph. In this context, we consider the Hausdorff measure with respect to the distance in Hn, and dm is equal to d if d is a number from 1 to n, and dm is equal to d plus 1 if d is a number from n plus 1 to n. These two definitions in the context of Heisenberg group are equivalent. This is proved by Franchi Serapione and Serra Cassano and Vittone, recently Vittone. Obviously, the C1 version implies the Lipschitz version, so the most difficult case is to prove the Lipschitz version implies C1 version. In general Carnot group of step 2, or step K, but also in step 2, these definitions are not equivalent. So the aim of my research is to choose some additional hypotheses in order to obtain the equivalence of these two definitions. Okay, I present the general case when G is a Carnot group of step K. The first ingredient is the intrinsic linear map. L from W to V is intrinsically linear map if it is closed with respect to the intrinsic dilation. That means that the graph of L is homogeneous subgroup of G. In this context, when V is horizontal, meaning that the Lie algebra associated to V is contained in the horizontal layer, it is possible to characterize the intrinsically linear map in terms of a matrix H times N1, where H is the dimension of V. Another important ingredient is the notion of UID map. Phi from W to V with 5, 0 is equal to 0. We say that phi is uniformly intrinsically differentiable at point 0, or in short is UID at 0, if there exists an intrinsic linear map satisfy these equalities. It is possible to define the UID condition at any point using the suitable translation map. In order to understand on Rn, this is equivalent to being C1 condition. If this concept exists, it is unique and it is called the intrinsic differential of phi at point A. When V is horizontal, the matrix associated to the diff5A is called the intrinsic gradient. The UID condition implies, when V is horizontal, implies that phi is intrinsically Lipschitz continuous. Implies that phi is 1 over k Holder continuous, where k is the step of Carnot group. Little meaning that it is Holder continuous, but the constant is infinitesimal. Finally, the UID condition implies that the intrinsic differential of phi at A or intrinsic gradient are continuous. So this is the first result. Let G a Carnot group of step K, V and W two homogeneous subgroup. V is horizontal and phi is a map from W to V continuous. The following are equivalent. The intrinsic graph is C1H regular surface if and only if phi is UID. The proof follows from implicit function theorem proved by Franchi, Serapione, and Serra Cassano and then generalized by Magnani, and the implication 2 imply 1 given by witness extension theorem proved by Franchi, Serapione, and Serra Cassano. An easy corollary says that if the intrinsic graph is a C1H regular surface, then its intrinsic gradient is continuous. So this is an important scheme of my research. If in Euclidean spaces we consider S the level set of C1 map and we wanted the gradient as maximum rank equal to K, in Carnot group we consider S the level set of C1H map from G to RK and we wanted the horizontal gradient as maximum rank equal to K. If in Euclidean space we consider S the graph of a map phi from W to V, where V is equal to Rk and W is equal to Rn minus k, and so we wanted V and W are complementary linear subspaces, and we wanted phi is C1. In the context of Carnot groups, we consider S the intrinsic graph of a map phi from W to V, where W and V are complementary homogeneous subgroup, and we want that phi and its intrinsic gradient are continuous. In Euclidean spaces, we know that these two definitions are equivalent. In Carnot groups, as I say, these two definitions are equivalent when phi is UID. The second step of my research is to characterize the UID condition in terms of existence and continuity of derivatives of phi. The first result is given by Ambrosio, Serra Cassano, and Vittone in the context of Heisenberg group. The first ingredient is the projected vector fields. This is a really hard definition, but it is really important in order to write explicitly the intrinsic gradient. So if G is a Lie algebra equal to the span of x1, xn, where x1, xn1 is a basis of V1, the intrinsic gradient is the 5 projected vector fields on W along the first n1 vector fields which generates W. This definition is given by Kozevnikov. I present the problem in the model case in order to understand. H1 is equal to W of V. H1 is R3. Identify R with R3. W is equal to the x of the span of x2, x3, and V is equal to the x of the span of x1. The only non-trivial bracket is the bracket x1, x2 is equal to x3. In this context, the intrinsic gradient is exactly the Burger operator. And my problem is to study the suitable solution of the Burger equation is equivalent to ask the UID condition. In general context, we ask the horizontal regularity and the vertical irregularity. We have G a Carnot group of step K, V horizontal, 5 a continuous function from W to V. The horizontal regularity says that our PDE system, that in general case is first order nonlinear PDE system, is satisfying the broad star sense if for every vector fields W belong to the Lie algebra associated to W intersecting the horizontal layer, and every point A, there exists a C1 integral curves of D5W starting from A, for which the fundamental theorem of calculus with derivatives omega holds. The vertical irregularity says that phi is vertically broad star order if and only if 5 along the integral curves of D5W, where W, the vector fields W, belong to the Lie algebra associated to W intersecting the other layer VD, with D is larger than 1, is little 1 over D order continuous, meaning that it is order continuous with infinitesimal constant. In the model case, the first Heisenberg group, the horizontal regularity, meaning that the Burger equation is satisfying the broad star sense if and only if locally around every point of W there exists a family of integral curves gamma of the Burger operator such that this equality holds. The vertical irregularity, meaning that 5 is vertically broad star order if and only if 5 is locally little 1 over 2 order continuous along the last component x3. So this is another result given joint work with Antonelli, Donne, and Donne. Let G a Carnot group of step K, V and W two complementary homogeneous subgroup. We ask that V is horizontal, 5 is a continuous map from W to V. The UID condition is equivalent to ask that 5 is vertically broad star order on U, and there exists a continuous function omega such that our PD system is satisfying the broad star sense on U. The next step is this question. Can we drop the vertically broad star order regularity in the statement C? One positive side is in Heisenberg group, Ambrosio, Serra Cassano, and Vittone, Bigolin, Serra Cassano, and Corni prove that if V is horizontal, it is possible to drop this vertical irregularity. On negative side, Kozevnikov proved that in Carnot group of step 3, when V is one-dimensional, it is not possible to drop this vertical irregularity, so it is necessary. Our result is in Carnot group of step 2, and V is one-dimensional. We prove that in this context it is possible to drop the vertical irregularity. So the UAD condition is equivalent to ask that there exists a continuous function omega such that our PD system is satisfying the broad star sense on U. This statement follows thanks to the free Carnot group of step 2. That's all. Thank you for the attention.
Okay, well, thank you very much, Daniela. So maybe we have actually time for further discussion and questions. So thank you. So are there any questions? So I actually, since we have some time, I would like to ask a few questions if you don't mind. So thanks. Okay, so maybe I'll stop the recording or pause the recording. So I paused it. Yeah. So okay. Well. So but thank you, Daniela, for the very interesting talk, and thank you everyone for joining. And we hope to see you in the next session of the seminar. So thank you again. So
Thank you. Bye.
bye bye. Yeah.